All right, so we're going to start with an example of buffer preparation sort of in the simplest possible way, which is how do you make a buffer solution when you have both the conjugate acid and base together. So you have them, you have bottles of both of them, and you can literally just mix them at the ratio needed to satisfy the Henderson-Hasselbalch equation. That's as easy as it gets, so let's do that real quick. All right, so just start by jotting down the Henderson-Hasselbalch equation. It looks something like this, and then I rewrote it in terms of the two species that we have here. So ammonia is going to be our weak base, ammonium is our weak acid, and we're given the Kb, so this just builds directly on the problem in the previous video of 1.8 times 10 to the minus 5. Remember, this was discussed in the previous video as well. Henderson-Hasselbalch is written in terms of pH and pKa, although you could rewrite this in terms of pOH and pKb, but that takes a little bit of effort. The other way that you can convert this, Kb, is just to write it in terms of Ka. And we know that Ka times Kb is equal to Kw, so we can quickly compute Ka. So the Ka is 5.6 times 10 to the minus 10 here. Negative log of that gives us the pKa of 9.25. Remember that pKa is with respect to the conjugate acid now, whereas the Kb was with respect to the conjugate base. And so it doesn't change anything, it just allows us now to use the Henderson-Hasselbalch in this form. So we can just plug in the values then, because we want a pH at 9, meaning we want to prepare a buffer solution in the lab with a known and fixed pH. This is really common in any biological sciences. You need to grow cells or whatever. You want a media, a place to grow those cells, that is intolerant or tolerant to any perturbations in pH. And so you'll often grow them in a buffer, and different organisms will thrive at different pHs. And so you'll choose buffer systems based on whatever that organism is. In this case, you want it to grow at an alkaline condition of 9. You know the pKa of this system is 9.25. So we can just plug those values in here. So we have 9, that's our pH desired, equals the pKa of 9.25 plus the log of the ratio of those two values. So we can solve. So that looks something like this. Remember, this is a log term, so to get rid of log base 10, we're going to do 10 to the value here. So we'll do that. And that gives us a value of 0.56. So what does that mean? Well, we can't go any further because we don't have any details about the particular species. But what we know is that we need to make up a solution where the ratio of the NH3, the base, and the acid is 0.56. And sometimes I like to write this more explicitly and write this because 0.56 is the same as writing it as 0.56 over 1. And what that tells me is I need 0.56 parts of the NH3 for every 1 part of the NH4. So that's the way that I like to think about this. So of course, actually making this buffer, we would need a little bit more information. We just know that this is the ratio, but what about the concentration? What's the final concentration of the buffer? Do we want to make a buffer at 1 molar, at 0.1 molar, at 0.01 molar, at 0.001 molar, etc.? It wouldn't matter. The ratio would be the same, but the individual concentrations then would be some fraction of that overall concentration. For example, let's pretend that we want to make a buffer with a concentration of 1 molar. What does that mean, a buffer at 1 molar? That means that the sum of both of the two species, the base and the acid, add up to 1 molar. So in other words, this ratio, we could think about it as a fraction that is a fraction of that 1 molar. So of this 1 molar solution, we need 0.56 parts of it to be, for every 1 part of the ammonium to be the NH3. So how do you do that practically? Well, there's a couple different ways. The first way that I'll show you is the way that I learned when I was an undergraduate, and it's a sort of intuitive way where we say, well, this is the ratio, 0.56 to 1, but what does that mean as the actual fraction? What fraction of the whole is each of these species? Well, if we're saying that NH3 is 0.56 parts and NH4 is 1 part, then what that means is total, there's 1.56 parts, right? Because each of them is representing these things. So that means that the fraction of ammonia is going to be 0.56 over 1 plus 0.56, and we could say times 100%. And similarly, we could write that out as NH4 plus is got to be equal to 1 over, because 1 part over the same total times 100%. These two things will add up to 100%, and we'll see what that gives us. So that tells us in the solution, what we actually have is 36% ammonia and 64% ammonium in order to achieve a pH of 9 for this system. And so if we want a total buffer concentration, which is really just the sum of these two things, to be 1 molar, then we can just take that 1 molar times 36%, that tells us how much NH3 we need, and we could take that times 64%, and that tells us how much of the other species we need. In this case, the numbers work out really conveniently because I just chose 1 molar, so that just means that we need to make up a solution that is 0.36 molar ammonia and 0.64 molar ammonium. Together, these add up to 1 molar, so our buffer concentration is 1, and the ratio of these two things gives us a value of 0.56, which is what we need to maintain a pH of 9. So that's an example. That's the first way that you could translate this ratio into a real concentration. The second approach is also quite straightforward, and it's just an algebraic one, but it requires two equations because we have two unknowns. You imagine this is this NH3 is like X and this NH4 plus is like Y. How do you solve for X and Y? Well, you need at least two equations with X and Y in them, and then you can solve a system of equations. And so we have this equation, which we could just sort of rewrite so it looks more like an equation. So we could just say, you know, this is 0.56 times ammonium equal to ammonia. So all I did was just take the ammonium here in the denominator and multiply it. So that's an equation. We need one more equation, and if we're still thinking about the same example where we want to make a 1 molar buffer, remember I told you what that means is that the sum of these two things adds up to the total concentration. And so the sum, that's implying another equation. We know we could write that out then as NH4 plus NH3, that means sum, is equal to whatever that buffer concentration is. Now we have two equations, two unknowns, so we could take, for example, this equation, this first one, which is already in terms of NH3, and we could substitute this term in here and solve for NH4. So we do that real quick. So that substitution looks something like this. Now we have one equation in terms of one variable. So NH4 plus 0.56 NH4 equals 1. So that's the same as 1.56 NH4 is equal to 1, which hopefully comes back to what we did before with that ratio fraction. It's the same value, 1.56. And that gives us this expression, 1 over 1.56, which is exactly the fraction that we sort of intuited before, just by saying, well, that's 0.56 parts of this and 1 part of that. So really that means it's 1 part in 1.56 parts. It's the exact same outcome, which gives us the exact same fraction, which we would then multiply by 1 to give us 0.64 molar, and we know sort of by deduction then that the other amount needs to add up to 1, so that would be 0.36 molar. So those are the two different ways, both of which will always lead you to the right answer. You can use either, you can use both, whatever's convenient and more intuitive for you.